We're going to delve a little bit deeper into how reactions work by talking about something called reaction mechanism. To start this off, we're going to introduce this idea of elementary steps and reactions. One thing that, this is not something we discussed much, but let's go ahead and introduce this idea is that most reaction equations that we see that we've been working with over the months, those are actually not really how the reaction occurs. For example, I'm going to peek down here at this equation at the bottom. NO2 and CO produces NO and CO2. Now, it's kind of convenient, I guess, in some way. If you were to look at this, looking at how this happens, right? If you kind of follow the atoms, it almost looks like NO2, right? It gives up one of the oxygens, puts it onto a CO, and so as a result, you make NO, right? Because it lost one of these oxygens over here. And then CO2 is formed because the CO gained an oxygen. So it's just kind of like you just through an oxygen from one molecule to another. And in fact, that is the overall change that occurs. But in reality, there's actually several steps that are necessary. And that's what we're saying here. In reality, it's a series of different reactions that occur to really make this reaction look like it does. So that O isn't just moved directly from one substance to another. And what we do is we actually look at this using a reaction mechanism instead. That's how we better understand what goes on. This reaction mechanism is a series of steps by which a reaction occurs. So what happens here and then is also identifying some other terms. Each step, right? Each step of the mechanism is known as an elementary step or an elementary reaction, right? Elementary meaning basic, fundamental, which overall combines to make the overall reaction. Okay, let's see this in action on the next slide here. This is the overall reaction, same one from before. So this overall reaction is written out there. And like we said, it's not going to just be an O being tossed from one molecule to another to make some new products. It actually is going to involve this reaction mechanism. Right? So the word mechanism is being applied to the collective group of all these individual reactions. And each individual reaction is called an elementary step. So there's the first elementary step. This bottom one is going to be the second elementary step. So this reaction mechanism shows us what goes on in reality in a much more specific pattern. So what happens again to start is actually NO2 and NO2. These are the two molecules that are going to bump into each other. Now, some of you are wondering, well, where did the second NO2 come from? Remember, we're not really having a container that literally only has one molecule of NO2 and one molecule of CO. That's ridiculous. There's like billions and billions of each of these substances floating around. And it just happens that two of them bump into each other. So when these two bump into each other, right, we don't actually involve the CO. That's going to come later. So we're going to first start off by taking the NO2 bumping into each other. And you see here, actually, it turns to be a little oxygen being moved from one to the other. It doesn't matter which one gets which one. But one of the O's, let's say from this one, gets moved onto this guy. So you generate NO3 and NO. All right. Now, that's the first step of our reaction. Right? It's kind of like a little side path here. So what happens then is that your NO, right, this substance that's generated, that's actually one of the substances that's going to be in your final reaction. We'll talk about that some more later on, but you might notice that. But then what about NO3? Well, NO3 doesn't appear in the final equation, the overall equation. So the NO3 actually is going to appear here. This is the next step. We can erase these two. So NO3 actually gets used in the next step right here. So NO3 finally gets used with CO, right? Because before it was just kind of hanging out. But now it's going to be reacted with CO, and that generates NO2 and CO2 as a result. Well, what do we get out of this? Remember, CO2, that's one of the reactants, or excuse me, that's one of the products in your overall. So that's what that generates. And notice that you generally have all the parts you need. But let's make this a little bit more coherent. How exactly does this generate this, right? How exactly does this mechanism make the overall reaction? And that's, something that we write out on paper in a way that doesn't seem obvious, but we can actually do a little bit of math in a way to make this work out. So as always, right, these little reaction arrows are kind of like equal signs, and we're going to kind of combine these and basically see what you can get rid of. So what appears on both sides identically that you can sort of cancel off? Well, NO3 is on the right side up here, NO3 is on the left side right there. So these two basically kind of ignore those. And then NO2 appears here, right? And NO2 appears on the right side of the other elementary step. So those two cancel each other off. So what you have left now, if you rewrite this, is NO2 plus CO yields NO and CO2. By the way, I'm leaving off the states that matter because, lazy. But you get the idea. Right, so the combination of these two elementary steps, right, the reaction mechanism, which is these two elementary steps, the result of which gives you the overall reaction. The next slide here gives us some terminology we need to introduce. The first one is an intermediate, or an intermediate. Now, most of us think of intermediate as like a level, right? You have a novice, intermediate, and then advanced or something like that. But intermediate in this context really means like a middle person or a middle thing, not a person, but kind of a step on the way. But it's actually a substance that's generated that is produced in one step anyway of the reaction mechanism. So like in one of the elementary steps, it produces the substance, but then that substance is then consumed in a later step of the mechanism. Right, so in a later elementary step. It doesn't appear as a reactant or product in the overall reaction. Let's scooch back up here and kind of see which one that is. So which one of these substances on this mechanism is actually generated and then later consumed? Well, the only one that seems to fit the bill here is NO3, right? Because it's produced in an earlier step and later consumed. So that's produced here in those one of the earliest steps, the first one. It's producing NO3, and then later on, you see right here, it's produced. It's used again in the next step. So it's generated here and then consumed in this next one. Well, what do you notice? Is it in the overall reaction? It's not, right? Because it just doesn't appear in the overall reaction, but it definitely was involved sort of behind the scenes. What about NO2? Well, NO2 is right here. You cancel it off the NO2 that was over here. But remember, right, NO2 is actually one of the reactants. Also, it's not produced in an earlier step, right? It's produced down here maybe, but it's not produced in one of the earlier steps. And so NO2 is not going to be considered an intermediate. Some other terminology. Molecularity. Molecularity is the number of species, and sometimes you see that word, which basically is saying which substance or which particle that collide in an elementary step. The number of particles that all have to collide to make it work. So you have unimolecular meaning an elementary step that involves just one particle doing something. That you don't have to have it collide with another particle. It's just itself just does something, like breaks apart or something. Bimolecular means that it has an elementary step that involves two particles that collide with each other, and termolecular is an elementary step involving three particles, which is fairly rare, right? Let's think about this. What's required for a reaction to occur? There has to be collisions with enough activation energy, all oriented the same way. So you can imagine maybe having two particles colliding pretty easily, right? Two particles bumping into each other. But what about three molecules bumping into each other, right? How likely is that three molecules all bump into each other at the same time? That's kind of difficult to imagine. But then don't forget, you also have to have the right amount of energy and also the correct orientation. They also have to be pointed in the right direction for the reaction to even occur. So that's why it's a fairly rare thing to see a termolecular reaction, a termolecular elementary step. But it's possible. So I'm going to scooch back up here. Let's talk about the molecularity of this example. NO2 and NO2. So we're going to look at this elementary step and take a look at how many particles it took for this first step to occur. The first one's going to be bimolecular. Okay, this is going to be bimolecular. Now, some of you may be wondering, okay, well, why that says bimolecular? But why is it that, if we have the same substance bumping into each other, shouldn't that be unimolecular? Well, remember, it's about the number of particles. It's not about the actual identities of what's bumping into each other, right? There's only one thing, technically, that's part of the elementary step as a reactant. But these are two different particles, right? So that's considered bimolecular. What about the second elementary step here? Right? NO3 is going to bump into some CO. That's going to also be bimolecular as well. That's a little bit better. So these two are both bimolecular elementary steps. Notice how we're not talking about the overall reaction, right? Because molecularity only refers to elementary steps, which you can see here. Again, the number of species that collide in an elementary step, not the overall reaction. So here's an example problem. I'd like for you to go ahead and give this one a shot. There are answers at the bottom, of course, but I'd like for you to try these without actually referencing those. But again, give these a shot, see what happens based on those discussions we just had. All right. Now, the whole purpose of reaction mechanisms is not just to say that there's some underlying reactions that occur, but there's also a relationship to that and the rate law. So mechanisms generally are useful, right? But we have to know that this is going to involve some guesswork. Let me go and tell you right now, you will never have to generate a mechanism. Right? You're not going to have to actually produce a mechanism where you have to write out a bunch of different reaction steps. I just want you to be able to interpret them. So we have to then also say, in order for a mechanism to be considered valid in the first place, by the way, one last thing I need to mention on this first point is that a certain amount of guesswork is involved. Like these are things that scientists have to sort of work out and hash out themselves, and that's not something that's very obvious. As you can imagine, trying to come up with a mechanism seems to have many possible different ways, and there's lots of techniques to get into it. We're not going to involve that, but the main thing is that if you do generate a mechanism of some kind, right, as a scientist, the one thing that has to be consistent is that the mechanism can be valid only if it's consistent with an experimentally determined rate law. Right? So we've talked about rate laws and how to get them. So your mechanism has to be consistent with that rate law. Right? If you have a mechanism that seems like it works on paper, but then you match it up against a rate law and they don't seem consistent, that's not going to work. We'll talk about how that's going to look in just a minute. And multi-step reactions, which is pretty much everything we're seeing here, multi-step reactions typically have one step, one of those elementary steps that are involved, that is much slower than the other, and this step is called the rate determining step. So let's use this analogy here. Let's say we have a road, right? It's got a highway, you have Plaza A, Plaza B for toll booths, right? And these process cars at different rates. Plaza A right here, right? What does it look like compared to Plaza B? Well, there's a bit of a backup at Plaza A. Plaza B doesn't seem to really have much of a backup taking the toll. So it looks like Plaza A is going to be a bit slower. That's going to be your rate determining step. Right? Sometimes it's also called the rate limiting step. What about example B, right? Plaza A doesn't seem to have a lot of cars backed up here. The second toll booth, the second set of toll booths, seems to have a little bit more of a backup here. So it turns out Plaza B, that's going to be your rate determining step, your rate limiting step. So the slowest step of a mechanism basically determines the overall rate. So the overall flow of this one right here is going to match the rate of A, of this specific step, of this plaza. Even though B seems to be doing the thing pretty well and pretty efficient, right? It can only go as fast as A is producing or is working. And in this one right here, right, the overall flow of this series or of this highway is dictated by how fast Plaza B can work, right? Because apparently it's not working very efficiently. Even though Plaza A is doing its business and spinning out, right, Plaza B seems to be slowing it up everybody. So again, this overall rate is dictated by Plaza B's rate. In that kind of analogy here, a chain is only as strong as its weakest link, right? So if a chain you have that you pull on it, you tug on it, if only one of them just seems to be just a little bit weaker than the rest, that one is going to break, and therefore the whole chain is strength is dictated by that one thing. All right, let's go and talk about this. First of all, this is going to be an example of a mechanism that generates some products, obviously, but this mechanism, you might actually find it to be kind of vaguely familiar. This mechanism is made of two steps. You have the first step here, the second elementary step down here, and they also label this as either slow or fast, right? So there's your slow rate determining step up here. This is your fast rate determining fast step here, and again, they tell you it's rate determining because they know that this is the slow one. This is the one that dictates the overall rate. Since the first step is slow, it determines the overall rate. The second step is fast and will quickly consume whatever NO3 is produced here in this first one. Now, how exactly the rate laws fit in though, right? So we're kind of just giving the overall idea of different steps in the rates, but again, how exactly we put this together, this is very simple. And this one you can probably been trying to do from earlier, or like looking at earlier rate laws, but very simple. The rate laws for elementary reactions are directly dependent on its molecularity, right? So basically it's coefficients that are there. Okay, compare this to rate laws that we looked at for overall reactions, right? This discussion up here that we're doing is for elementary reactions, but remember for the overall ones where we might have a balanced equation, we can't just use coefficients. Let's see how this works. Write the rate law for each of the following unrelated elementary reactions. So these are just three random elementary reactions. You might have picked them somewhere. It's got A and B's and so on and so forth. What's that going to look like? Well, the first rate is going to be related to A and B. So it's going to look like K times A, K times B. Okay, now how do I know for sure that the exponents here are 1 and 1? How do I know my rate order is 1 and 1? That's because for the elementary step provided here, again, I have coefficients of 1. So my exponents are going to be 1 and 1 for each of these. Also notice how I just say products. Well, because rate laws don't rely on the amount of products that are there. Right? It just relies on the amount of reactants. What is the next step right here? All right, this next elementary step, again, just some random elementary step. What's the rate law going to be for this one? It's going to be K times A to the second power times B with a rate order of 1. That's it, right? Because whatever you see is whatever rate law is going to be. It's kind of nice. But as a reminder, these are only for elementary steps. You can only do this for elementary steps, not for overalls. I'll give you a shot at trying the last one out. Now, this is an example again. This is your mechanism for a reaction. First, determine the overall reaction equation, figure out the rate law, and then identify intermediates. Okay, so how this is going to work. First of all, the overall reaction, again, we're going to look at what appears on both sides of these. NO3 seems to appear again. NO2 seems to appear again. So to have the overall reaction, it's going to be NO2 and CO, and it's going to produce NO and CO2. So this is what you would normally see just on any given day. But of course, there's a background, there's kind of an underlying mechanism that is actually happening that gives you this overall reaction that you just wrote out. All right, next one. What's the rate law for this reaction? All right, so what's the rate law for the overall reaction? Now, remember the conversation here is that we can look at the rate determining step of the mechanism and use that as the rate law. So as it turns out, the rate for this one is going to equal to K times NO2 squared. Right? Again, looking at our rate determining step, you see here it's got NO2, it's got NO2. Again, ignore the fact that it's crossed out because that's just for writing the overall reaction. And so you have two of them, right? And that's going to be then 2 NO2 yields yada, yada, yada. So as a result, you have 2. So that's going to be your rate law, not only from this first step, but also now for the entire reaction. So this is now the rate law for this whole reaction. Why does it not involve CO? Well, because CO is not involved in the first step. Right? CO is involved in a later step, in a faster step, which is not a part of the rate determining step. So it's not involved in this rate law. It's going to be 0 order to CO. So what does that mean? That means you can change the concentration of CO all you want, carbon monoxide all you want, and it's not going to affect the overall rate. Finally, identify intermediates. We did this before, right? So we saw that NO3 is produced in this first step. It'll be consumed in the next step. That's going to be your intermediate. Okay, you have another example here. Go and give this a shot. This is, again, a reaction mechanism provided to you. And essentially, you can do the same thing. Write the overall equation, write the rate law, and then figure out your intermediates. Right. Some of you may be wondering, well, what if you don't have a first elementary step? That's actually the slow step, the rate determining step. There is a fast initial step, right? In this example here, this is one that we could look at later on, but you got NO and BR and so on and so forth. You have yada, yada. And all this stuff right here, again, this is a mechanism that you could use to figure out rate laws and such. But what you notice here is that the second step is a slow step. So like the latter step is the rate determining step. Unfortunately, we don't have enough time to get through this, so it's actually a little bit more fun, to me anyway, but that's going to be something that you can do in AP Chemistry. So again, if you have a fast initial step, we're not really going to be doing it. We'll only be doing ones that have, we're dealing with a mechanism anyway where the first step is the slow step. All right, that'll do it.